Let's switch directions. Our vector valued functions have a single variable input and multiple outputs. So we had a function f of t, g of t, h of t, and we called that the output r of t, but that's a single variable input. So r here is acting as a function from one dimension to three dimensions. So the input's a real number, but the output is an ordered triple. I want to go the other way. I want a function whose domain is two-dimensional and whose output is one-dimensional or more. Now, for our purposes, we'll primarily stick to R2 and R3, but the same thing applies to any dimension. And that's a multivariate function, a function of multiple variables. So now we're only getting one number out, but it depends on multiple inputs. You experienced this today. What's wind chill? Aha. So the wind itself changes our perception of the temperature. And so that means that there are two things that we depend on. It's a function of what the actual temperature is and a function of the wind speed. Two inputs, one output. And depending on the actual temperature and the speed, we get a different apparent temperature, the feeling outside. Page 889 shows me a table. Actual temperature, Celsius, real degrees. Wind speed, kilometers per hour. If it's 5 degrees out with a slow wind of 5 kilometers an hour, well, it'll feel like 4. It won't actually feel like 5. But if it's -5, like it was this morning, and we have these gusty winds of 20 to 30 kilometers an hour, it could feel between -12 and -13 as you walk across a lot. Ugh. That's a hell of a jump, isn't it? And notice that as the wind speed gets faster, even if the temperature remains constant, what we feel changes. So that's a function whose input is two-dimensional and whose output is one-dimensional. You have to give it the actual temperature and the wind speed, and then it will give you the apparent temperature. Now, I don't have a formula for this, but I could write formulas that are functions of multiple variables. Something like this. Now, I pulled this out of thin air. I freely admit that. But I can ask the same question as I would back in Calc 1, hell, as I would back in an algebra class. This is a function Functions have domains and ranges and codomains and all of these properties that I like about functions. I should still be able to do that. But my domain in this case is a set in the XY plane. It's not a region of the line from 1 to 7 or -5 to minus infinity. It's an actual physical two-dimensional region. So how would I find the domain of this function? A definition of domain is the set of numbers that make sense when you plug it in, right? So what's the first thing you can guarantee me is going to fuck this up? But more specifically, X being 1, right? Now, remember, I'm thinking of the domain in X and Y. So the set X is not equal to 1, or the set where X is equal to 1. The set X equal to 1 is a line. It's a vertical line at the height 1. This is X equals 1. And I don't want that. I'll make it a dotted line. That's the part I cannot have to start with. But there's more. That would cause me to divide by 0. What else might screw this up? Aha, if I have a negative under the square root. However, x squared plus y squared is always positive, right? And then I'm adding 1, so that's okay. So this always works. And that means that the only problem points we have are here. Everywhere else in the xy plane, if you picked a point, you could plug it in, you could get a value, right? Okay. So finding a domain is really a combination of all the tricks we learned back in algebra class to find domains before. Same question. Here's a function, f of x, y. What's its domain?
look at like you equal the square root of 4.5. Wait, never mind.
Walk me through how you get there, Jack.
Well, I was thinking like it can't be 0 underneath the square root.
So I need this to be bigger than or equal to 0, right? Which means move the negative stuff over. If that was just equals, not less than or equals, if that was 9 equals x squared plus y squared, what would I have?
The square root of 1.5.
Not necessarily. Because I can't distribute the square root that way. But what that's a shape I recognize, that equation. If I just look at equals, x squared plus y squared equals 9. What shape is that? Circle and center at?
0.
Aha. So less than or equal means I want the inside of this. Questions so far?
The domains like dependent on each other. Next, so this
There's only one domain. It is a set in x and y. And those variables are related to one another through that equation, right? The distance from the origin must be less than the square root of 9. So I should get a single shape. But if you want to think of them kind of independent of each other, in this case, they aren't. X and Y are dependent on each other, as opposed to the wind chill factor idea, where the wind speed and the actual temperature really don't care about each other. They behave on their own. Here, X and Y actually do get connected. Let me give you another example. Two economists. Cobb and Douglas. They came up with this idea that the production level relates to both the amount of labor you have available and the capital investment you have available. And it turns out that they actually said, well, both of these should never be 0. If you have all labor and no capital, then you're a slave owner. If you have all capital and no labor, you're a rich guy with nobody to work for him. You're not making very much, right? And he said, well, Cobb and Douglas together, they looked at data for a number of factories from a bunch of different years, and they came up with a model that said the production is some constant B times L raised to the alpha and K raised to the 1 minus alpha. And alpha has to be between 0 and 1. These are power fit curves. They literally did this as a statistics example. They went back and they said, hey, here's a model. And they showed how you can increase labor and get a higher return. You can increase capital investments and get a higher return. But they play off of each other, right? If you spend more money, you have less money to hire people if you spent it on equipment. And if you hire more people, you might not have as much money to renew the equipment. So there's a trade-off here, and that's why those powers are related to one another. Here, again, the two items definitely depend on each other, and there is an upper limit to each of those, right? There's a maximum amount of labor you can purchase. There's a maximum amount of labor your facilities can utilize. There's a maximum amount of capital you can raise to invest. Theoretically, we all saw what happened when Musk bought Twitter. So you can raise a lot of money, but that's how you do it. Are these independent of each other? Not really. But you can treat them that way in the theoretical behavior. Better?
Yeah.
More questions? Of course.
So when I took something, I was thinking like the x squared or the negative x squared minus y squared have to be less than 9. So you don't get a negative, but
So-
can you take a piece of that?
Well, what you just said is exactly the algebra we did here. You said, oh, well, that has to be less than 9, right? Well, what happens when I switch the negatives? And if I move the minuses, well, I get exactly this expression. So I'm absolutely agreeing with you. That's exactly the right way to see it. This stuff can't be negative. So if I write the negative x squared, that can't be bigger than 9. It's got to be less than 9. Move the negative to the other side, and I get exactly this equation. Yes, yes. More. Okay. It's a pretty picture. I have this equation. I find a domain. I draw a little shape. So what? We have in that equation we know our domain is the set of xy so that x squared plus y squared is less than or equal to 9. And we know that that's the picture of the circle of radius 3. Right? So our function lives here. If I was just going to be an algebraist, I'd be done. I'd walk away and say, that's all I need to know. I don't even need the picture. I need that. Its domain is this set. But I'm a very visual person. So let me try and figure out how this looks. What does this graph like? Wait a minute. Wait a minute. How did we draw a graph again? We looked at all the inputs, looked at the outputs, right? But now my input is in X and Y already. Where's my output? You knew that. I can draw another axis perpendicular to that and say I'm going to have a graph over or under or somehow contained to this area in 3D. Page 890, figure 4, bottom left corner. Here is my overarching idea for a graph. In the XY plane, I have the domain, this yellowish, orangey sort of shape here. And then I plug in numbers and I get out a new value, and I will graph that as Z. So I will graph to each of these points a corresponding three-dimensional point, X, Y, and then the height, f of X, Y. So I'm going to associate in my head Z values with outputs, just like in algebra class. I said, oh, each X has a Y. Well, now each XY gets a Z. And so I end up with a graph that isn't a curve, it's a surface. And that's why we've written up here S. That surface, S, lives over my domain, D. Here's our domain, the circle of radius 3, right? This domain right here, that's our picture for the function we were just looking at. There's my picture. So now I'm going to put that in 3D. In order for me to draw this correctly, I need to draw the circle of radius 3 in the XY plane. There's my circle in the XY plane. And now I can say whatever graph we have, matter of fact, I'm going to do this. Over here in my circle, I'm going to draw the letter D for domain. Right? Now here's a perspective shift for you. I'm going to put that D in this circle. Where does it go? The vertical here is along the Y direction. That's this way. The letter D got turned. That's the Y direction, and that's the X direction. I had to move. Changes my headspace a little. I got to pay attention to that when I move this drawing from flat to three-dimensional. I am a crap artist. I freely admit that. I should still be able to tell you what this function looks like, even if I can't draw the picture. But I'm associating F output with Z. So I could take this equation and rewrite it. Z equals square root 9 minus X squared minus Y squared. And all of a sudden, I get kicked in the back of my head from a memory that goes, hey, wait a minute, you know this. If I got rid of the square root, how could I get rid of the square root? So I'd square everything and end up with a Z squared. If I end up with a Z squared, then all of a sudden my brain goes, that's a degree 2 equation. That's a quadratic surface. Chapter 12, section 6. I can draw the picture. I don't have to draw the picture. But you should be able to tell me what shape it has without drawing. What shape is this? Why?
Very positive. Issues.
If I move everything to one side, absolutely. But now I can go a step further. That's not just any ellipsoid, that's special. It's a sphere. So it's an ellipsoid, but it's a circle. It's the same direction. So it's 3 to the left, 3 to the right, 3 to the front, 3 to the back, 3 up. Wait a minute. Should it be 3 down? This equation is 3 down, right? But that's where I started. When you take a square root, you only get one of the two numbers, right? So really, I only want the positive z part. I don't want the negative z part. Remember, when you square an equation, you add extra solutions. That was way back in algebra class. Long time, it's probably gone by now. But it should be a function, right? When we were doing functions and graphs, we said there was this vertical line test. What's the vertical line test again? To be a function, a vertical line only crosses once. But now my vertical lines are in the direction of the z-axis. So each z, there can only be one z for each point. So I can't go 3 down, I can only go 3 up. This isn't the whole sphere, it's only the top hemisphere. Now, I would love to assume that I am right. But I don't buy it. How do I know whether or not I'm right? I'll draw the picture. But I won't draw it myself. I'll let the computer draw it for me. So you'll notice it's even written automatically z equals. It assumes I'm going to try and draw a three-dimensional graph of the form z equals stuff. So let's put in exactly the equation we were just looking at. Over here, that little sigma symbol, that's where all of my symbols are hidden. So I can click that and I can get a square root. Square root of what? 9 minus x to the second. I got to come out of the exponent. Minus y to the second. And if I've drawn this correctly, I should get an upper hemisphere. What's wrong with my picture?
It's, like it's not circular at the bottom.
Because the bottom is still thinking in grids, right? In X and Y. As a matter of fact, if I look down at this, see how it's thinking in pixels? Yeah, so it doesn't quite make it to the circle. If I zoom out a little, no, that doesn't help. Zooming in gives me, no, not quite. Yeah, it's not the greatest picture. I might be able to change the way I graph by thinking, instead of in X and Y, thinking in round, but I don't know how to do that yet. So we're going to leave that alone. It's a shame. It would be so nice if it worked perfectly, but no. The restrictions, though, are our grid. So if there was a way to adjust our grid, we could fix that. There may very well be, I just don't know what it is. But as we see, this is a crappy sketch too. So how else could I know what this shape is without relying on the computer? Meh, all right, that didn't work very well. What else could I do? Well, there are lots and lots and lots of good 3D graphing software. I don't typically use the one on Grapher because of that chop off, but for all of $1, I bought a piece of graphing software called Quick Graph. Excuse me for a second. There, now you can see my screen better. Quick Graph actually allows me to do 3D graphs as well. See, there's a little thing right there that says 3D. If I poke that, I can add an equation here, and it's color coded. X is red, Y is green, and Z is blue. Add an equation, Z equals, just like before, square root of. Now, this doesn't put the roof on the square root automatically, right? It shows me what it looks like down there, but up here, I don't see that. So I got to be careful. Minus X raised to the second minus Y raised to the second. See, that's not what I wanted, is it? So what I need to do is I need to say square root of all of this thing with a set of parentheses. 9 minus X squared minus Y squared. Close my parentheses, and that looks like what I want it to look like down there. So when I tell it I'm done, again, better, but again, we see the same sorts of artifacts on the edges because it's still thinking in grid. The reason I like this is it's a little more intuitive to move stuff around. I can change this to show some different pieces. I can display the axes. Where is my wireframe? There it is, appearance, wireframe. So we can see the grid itself, right? I can do just points. I can do a solid surface with the curves on it. There's my grid lifted up. I can change color, do all sorts of things, right? It's up to you as to which one of these. I know the grapher is built into the MacBook. You might as well use that one. But I tend to use this one because it's a more intuitive interface. Mathematica, derived, yeah, go ahead. GeoGebra. Google itself will draw these. If you type in graph Z equals, and then type in the equation we did, in Google, it'll draw you a picture. Page 892. Lots of different pictures. Whoa. All right, wait a minute. What's going on here? Those top two are the same picture, just looked at from two different perspectives. X squared plus 3y squared times e to the minus x squared minus y squared. I'm just looking at it here from above and here from below. So those are actually exactly the same picture. Where am I going to see something like that? That's a water molecule. Polar dipole with a valley in the middle of it, right? And a ground state further out. I'd love to tell you this is useless. Sine x plus sine y, that's periodic in both directions, isn't it? Sine x, sine y, so multiplying divided by xy. Wait a minute. There's a domain issue here. What's the domain problem here?
X, Y, 0.
If X and Y are 0, I'm in trouble. If either of them are 0, I have a divide by 0 here, don't I? So I have to figure out why there are no holes in this picture. Sine X over X. What did we do with sine X over X back in Calc 1? We did limits. And the limit as we went to 0 of sine X over X was 1. So there's something going on here with the limit. Oh, I got to do more calculus here. I got to do more calculus here to figure out what the hell's going on here. I like these pictures, but I rarely carry a 3D grapher with me. So how could I draw this without technology? Or at least let's get an understanding of what we can do without technology, even if we don't actually draw the functions all the time. You did this already. We just didn't think of it as functions. I'm going to take this equation and I'm going to cut it. I'm going to slice it. But I'm going to slice it parallel to the XY direction at different heights. And if I can figure out what's going on at each height, then I know what this graph looks like by stacking all of those shapes one on top of the other. Again, I've done this before. Here is a mountain. And each of these red curves are at the same height. This darker red curve here in the inside, that's at 5,500 feet. This one is at 5,000 feet. This one is at 4,500 feet. The blue are creeks, but these are level curves. They're a curve cut at a particular height. This is a topographical map. So right here, where all of these are marked as changes in height. That means that right here, this side of the mountain is pretty steep. There's a lot of changes in height in a very short horizontal distance. But over here, the change in height is not as much because these levels are further apart. It takes a lot further to go down 100 feet here than it does here. At point A, we're climbing faster or falling faster than we are at point B, depending on which direction we're going. And if I happen to be marching this way, I might not be changing height at all. So this idea of level curves allows me to create a topographical map of my function here. So let's do that for this function. I'm going to create a set of level curves. I don't know which of us that was. I do that by setting f of xy equal to a constant, where that constant is permitted by my domain. Now, my first reaction might be, how the hell do you know what k's should be? Well, that again is algebraic, right? I look at this and I go with Nora's statement, hey, I can't have that be smaller than 9, right? As a square root, I probably shouldn't use a k any bigger than 3. So let's start with what happens if k is equal to 3. Well, then I would have 3 equals the square root of 9 minus x squared minus y squared. And that describes a set of x and y in the plane. So let's solve for x and y. All right, I square both sides. I move the variables from right to left. I move the 9 from left to right. And I get x squared plus y squared equals 0. What set of x and y satisfy that? Just 0. So there's a single point where k equals 3. So that means at a height of 3, there's a dot. Now, do you want to go up or down? Say again? Down. So if I go down, where do you want to go? K equals? Pick a number. 2. 2 equals square root 9 minus x squared minus y squared. So I square both sides. Move the variables over. Move the 4 over. What's that? What shape is that? A circle of radius square root of 5, right? Square root of 5 is 2.24-ish, I think. So there, square root of 5. So we come down 1 unit, we go from a dot to this circle. If we keep going down, right, k equals 1, we'll get a bigger circle. Now the square root of 8 is like 2.8. So when k equals 1, we're out here. And yes, I know I'm putting them on the same axes. That's actually encouraged. Like our topographical map. When k equals 0, what circle will I get when k equals 0? Right. And if I let k be negative, when I get negative number equals the square root, I can't do that. And if I let k be bigger than 3, I'm going to get x squared plus y squared equals a negative number. I can't do that either. So this only works to describe a series of concentric circles. Now you could fill in other numbers, right? You could pick k as 1.5 or 2.3 or whatever, and you could figure out more level curves, and then you could stack them up. Where have I heard or seen of someone doing this before? Eek, what the hell happened? It in here? Here it is. I have put this video on our Canvas page. What you see on the left side of the screen is a pencil cup. My friend Robin designed this in a 3D printer. It's an ellipse that's twisted and then rotated around a bunch of times. It's a very pretty thing. I have like 8 of them sitting in my office. I will bring one. I forgot today. But on the right, you see the actual commands sent to the 3D printer. Print this shape at a height of. That's the bed height. So this is the solid bottom of this cup. And if I hit play, it will play through going up and down in Z values. And on the right-hand side, what will we see? We'll see the level curves. As he drags that pointer up, that's where your 3D printer deposits plastic on a level curve of your surface. Ladies and gentlemen, this is how 3D printers work. They slice up your function, and this is called, there we have a left corner. It's called the slicer. I wish I was making this crap up. That's exactly what it's doing. It's building a set of level curves and then printing them. Now, some computers will also say, oh, well, you're going to need support material for stuff underneath, in which case it'll add those to the level curves, and they ought to cut that out. But this prints with no support. So you print that shape, and that's exactly what you get. No extra bits hanging off, holding it up. It prints in one piece. But it does that by doing this. Slicer takes your solid object and turns it into a set of cuts. And it then deposits plastic at each of the right spots. Level curves. Temperatures. Isotherms. If these were wind speed, then these be, or air pressure, these would be isobars. And that's what tells me where the wind is going to be fastest. When we move from high pressure to low pressure, and all those bars are really close together, like the heights falling down. Here is a set of level curves. One problem, there are no numbers on that picture. Some graphs will use one color to indicate a positive number and one color to indicate a negative number. They'll put a color scale on the z-axis, but I don't know which of these go up and which of these go down. But they go in both directions. Same thing here. One of these is up and one of these is down. This is an electric dipole. If I move from 2 variables to 3 variables, well, then instead of level curves, I get level surfaces. I'm going to go for a dip in the pool. This is psychotic. It's freezing outside, right? But I could ask you, what's the temperature in the pool at any given point? Well, then I'm going to have an X, a Y, and a Z, and I'm going to have a T of X, Y, Z, a temperature based on where I am in the pool. Height matters as well, right? I let loose a CO2 canister in the corner of the room. What's the density of CO2 at any given point in this room is a function of 3 variables, isn't it? Somebody threw out a tuna fish sandwich in the garbage can. Measure the stink at every given point in this room, right? Depends on where you are, doesn't it? So now I have a way of thinking about functions as a function of multiple variables. We can also think of these, remember when we called the function r of t a vector value function? It was a function that put out a vector. The value that came out was a vector. Now these are vector input functions. So they're vector functions. Functions of vectors is what transformers use. You know, general purpose transformer, GPT. This is what machine learning is built on. Every AI system in the world thinks as functions of vectors, and that's a multivariate function. And the functions we are creating transform vectors right now from vectors to numbers. There are functions that go from vectors to vectors. That's linear algebra. So if I can do this, I need to be able to do calculus on this stuff. And that means I got to go back to Calc 1, which means limits, derivatives, eventually integrals, all of that stuff. I got to figure it out. This is where we're going to start. I will see you all on Wednesday. Have a wonderful rest of your day.